Today we're going to be talking about differentiability, or basically that means where can you take the derivative. So you can find the derivative of a function at any of the points unless one of the four things happens to our graph. So we'd have to look at a graph of these to figure this out. A corner, now think about what function we know looks like a corner. Most common should hopefully come to mind, the absolute value function. A cusp, but I'll show you guys when that happens. A vertical tangent line. And 4 is probably the most common that we're going to be seeing. And that's going to be a point of discontinuity, where the function's going to jump, or the function's not going to have a value. So the first one, a corner, is when the one-sided derivatives differ. If you think about the absolute value function, an absolute value function can be written as a piecewise function where we have negative x, it's the line y equals negative x for x is less than 0, and it's the line y equals x for x is greater than or equal to 0. Well, the slope of the line y equals x is negative 1 versus the slope of this line is going to be positive 1. So that's why we're not going to be able to take our derivative at x equals 0. A cusp. So when you are looking at this, your slopes of your tangent lines here, we're going negative, 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 but compared with, say, this tangent line over here, with maybe one that's real close to 0, those tangent lines, that's not as steep as this one right here. So our secant lines are approaching negative infinity from one side, and then another side, it's going to be approaching, say, this tangent line here, it's approaching positive infinity as I get closer and closer to 0. A lot of times this happens when your function, the exponent, is a fractional number. A vertical tangent is where the slopes of the secant lines are going to either approach infinity or negative infinity. So let's look at what our slopes of our tangent lines could look like for this function. So right there, that slope right there is something that's pretty shallow. It's positive, but it's pretty shallow. Now, maybe that's closer to 1, versus this slope was maybe something like 1/4. This now is closer to 1, but as I get real close in here, its slope's getting closer and closer to a slope of a tangent line that would be a slope of a line that wouldn't exist. So this slope of each one of these tangent lines is getting bigger and bigger and bigger. A lot of times that's going to happen with cubic root functions, or say fifth root functions and different functions like that. And then a point of discontinuity, where from the left and the right, where you're going to jump functions. A lot of times that happens with piecewise functions. Okay, we want to show that the function is not differentiable at x equals 0. So let's use the limit as x goes to 0 from numbers a little bit less of our function. So of our function minus f of 0 all over x minus 0. Now what function are we going to use from numbers a little bit less? We're going to use the top function. So using the top function, we have our function is 3x squared. The function evaluated at 0 is 0. Simplifying inside that limit, we're just going to have 3x on the top. So that limit is going to be 0. So our function from the left the left derivative at x equals 0 is 0. Now let's look at the right. So our limit as x goes to 0 from numbers a little bit more Okay, so for numbers a little bit more, we're going to use the bottom function. That's going to simplify to 3. So our limit is 3. So our right derivative at x equals 0 is 3. Since the left derivative and the right derivative are not the same value, 0 is obviously not the same thing as 3, our limit or our derivative doesn't exist. If you were to graph that function, think about it. We would have so for numbers less than 0, we're going to have a parabola, something that looks like a parabola. And technically that should be an open hole. And then for numbers greater than 0, we're going to have a line. So two different functions meeting, derivatives are not the same, so therefore we do not have, our function is not differentiable. Okay, next one. At what points does the function appear to be differentiable? So where can I take the derivative? So looking at this graph down here, it looks like our key points are going to be at -1 and at 2. And just looking at this, does it look like I can take the derivative at -1? Well, all of these slopes of the tangent lines would be positive for numbers less than -1. For numbers greater than -1, they're all something negative. So I'm not differentiable at -1. So from -infinity to -1. Also, I am differentiable from -1. Notice how I'm using interval notation, not inclusive, from 1, 2, since 2 is a point of discontinuity, to 2, and then in union with 2 to infinity. Now where am I continuous but not differentiable? That happens at x equals -1. Because at x equals -1, yeah, my left and right limits equal the function value, but I can't take my derivative there because the derivative, it looks like, from numbers a little bit less is positive, from numbers a little bit more is going to be something negative. And where am I continuous and not differentiable? I'm continuous. I'm neither continuous nor differentiable at x equals 2. Because we have the jump, and because it is not continuous, I therefore cannot take our derivative, which leads us to our next slide. Differentiability implies continuity. So if you can take the derivative, so if a function has a derivative at a point, then our function has to be continuous at that point. So if I can find the derivative, I can find I'm continuous. But not always. Continuity doesn't imply differentiability. And the last graph was a good example of that. Also, an important theorem that we have is intermediate value theorem for derivatives. Remember, we talked already about the intermediate value theorem for continuity. So if a and b are 2 points on an interval for which f is differentiable, so I'm also continuous, then our derivative takes on every value of the derivative from f prime of a from the derivative at a to the derivative at b. So real quick, what that means. I have a function from a to b. And let's estimate what the slope of that tangent line could be. Let's say the slope, or f prime of a, it's something positive. Let's say it's 1/2. And f of b, oh wow, that's a really steep value. F prime of b, I'll say that that's something like 5. We know then that the derivative for all the points on this function here, I'm going to have a value for the derivative. The derivative is going to take on every value from positive 1/2 to 5 along that interval. Now you can see for part of this here, part of it we're negative. But I know for sure, because our function is differentiable for all these values, I'm going to have a value of my derivative be between 1/2 and 5 for all the values. Okay, please make sure your lesson summary is submitted on time.